So Ron, for many years, you and your laboratory group have done a great deal of work to define the way that insulin works in cells, the signaling pathways in cells. But more recently, you've been looking at the effects of insulin resistance in different specific tissues by knocking out the insulin receptor in transgenic mice. I know you've knocked out the insulin receptor in many tissues, including muscle, adipose tissue, liver, even endothelial cells. So can you tell me what you think is the most important tissue in insulin resistance as it relates to the development of diabetes and the metabolic abnormalities we see in type 2 diabetes?
So this is actually an interesting question because we know that at a physiologic level, when we study patients with prediabetes or early diabetes, the earliest detectable defect is defects in glucose uptake into muscle. But when we do our animal studies knocking out insulin receptors, knocking out insulin signaling in muscle has a very minor effect. The major effect of knocking out insulin signaling in muscle, besides decreasing glucose uptake in muscle, is to actually shuttle some of that glucose into fat and increase fat storage. And the three tissues which have the greatest effect on glucose metabolism directly are actually the liver, the beta cell, and the brain. And let me just comment briefly about each of those. The liver obviously is where insulin is suppressing hepatic glucose output, and this is a very major part of course, the early hyperglycemia, fasting hyperglycemia that's present in type 2 diabetes. The beta cell is interesting because actually what insulin does at the beta cell is it actually helps allow glucose to stimulate the beta cell. So if you deprive the insulin signal, then the cells lose their responsiveness to glucose. And that's, of course, another defect in type 2 diabetes, the loss of glucose-stimulated insulin release. And the brain is probably the most interesting and hardest to study in humans from a clinical purpose, but it's very clear in these rodent studies that at the level of the hypothalamus, insulin signaling not only plays a role in appetite regulation and satiety, but even a direct role on peripheral metabolism, probably through the sympathetic nervous system. So if you knock out insulin signaling in the hypothalamus, even in the few neurons that are producing, for example, AGRP, one of the peptides involved in appetite regulation, you not only have effects on appetite, but you actually directly affect the ability of insulin to affect hepatic glucose output. So if I had to say what tissues are the most important, it's the liver, the beta cell, and the brain.
So insulin has direct effects on the central nervous system and also affects glucose metabolism in liver and other tissue, obviously other tissue in the body, but particularly you say the beta cell is very important, glucose uptake in the beta cell and glucose output from the liver. But you've also, I believe, found major changes in lipid metabolism in some of these models. So is diabetes involves more than just glucose metabolism and appetite?
Yeah, sure. So with lipid metabolism, I like to say that there are really three different kinds of defects in the metabolic syndrome that we have to look at to some extent separately. Obviously, one is in the circulating lipids, cholesterol and triglycerides and the lipoprotein distribution. The second is lipids accumulating in the liver, hepatic steatosis. And the third is actually lipids making it into the bile in terms of cholesterol, which can put you at risk for gallstones. And what we've shown actually is that at the level of the circulating lipids, insulin resistance at the liver is clearly a major factor for low HDL and small dense LDL, VLDL. It is not the insulin resistance, however, that causes the hypertriglyceridemia. It causes actually the change in balance of cholesterol-containing particles. And it's probably a combination of insulin resistance plus hyperinsulinemia that actually leads to the hypertriglyceridemia, which we don't see when you make pure insulin resistance. But insulin resistance at the liver will not only affect LDL and HDL patterns, it will also lead to increased cholesterol secretion into the bile and decreased bile acids, so animals are at greater risk of forming cholesterol gallstones. And it will also impact on hepatic lipid accumulation, sort of fatty liver.
So these models of insulin resistance in different tissues have really elucidated a lot of the pathological and pathobiological mechanisms that we see in people with type 2 diabetes.
Oh, very much so. And I think that although the mouse is not certainly a perfect model for the human in many different ways, it has allowed us to get an insight where we can now design specific experiments to look in humans to see are these processes there. And in many cases, we're actually discovering processes that we didn't previously recognize. I would also comment with regard to your comment about these non-classical target tissues for insulin action, like the endothelial cell, the brain, the macrophage. All of these actually do play a role. And of course, many of these are difficult to get access to in the human, but can be studied very well in the rodent models and then lead us to new ways to test humans to see what their role might be.